this video, we'll be going through the AP Physics 2 2022 FRQ exam. And without further ado, let's just dive right in. So let's begin with problem 1. Before I even look at the text describing the problem, I'm not even scrolling down there. We'll begin by looking at our diagram. I can notice there's a laser setup and a screen setup, which makes me think potentially that we're dealing with double slit interference. There's a suspended block in a fluid, so we might be thinking about buoyancy. And then because there's a laser in air entering water, I am also going to be thinking maybe Snell's law is relevant. Okay, let's keep going and see if the paragraph text supports that. So students are investigating electromagnetic wave phenomena in transparent media. That looks like that might relate to Snell's. They use a string to support a stationary thin rectangular block of mass mb, volume v block, and density rho block. And so that strongly supports our prediction that maybe we'll be dealing with buoyancy. The block has two narrow slits. That suggests we'll be dealing with double slit interference and is submerged in a glass tank containing water with density rho w. All of this we've determined before actually looking at any questions. And now this is up to you, but often it could be helpful to even pull the relevant equations before you go on to the next part. But I'll start by going on to the actual questions. And so let's begin with question 1a. We're asked on the dot below, which represents the block, draw and label the forces that are exerted on the block. And indeed, this seems to support that we are dealing with a buoyancy question, because what forces will act on our block? Going back to our diagram, we can see it's supported by a string, which will exert a tension force up. So we'll have tension. Then we will also have a buoyancy force up. So let me actually lessen the length of that arrow, F buoyancy. And then lastly, we're going to have force of gravity going down. Of course, for the actual AP exam, you want to be a bit better with your labels, right? So writing F gravity, F buoyancy, and F tension. Excellent. And notice we're not explicitly told that these must be to scale, but it's just good practice in general to have it be somewhat to scale, right? So you'll notice that my tension and buoyancy forces are shorter than my gravity forces so that it is plausible that they all cancel out. Okay, part 2 is asking us to derive an expression for the force exerted on the block by the string in terms of the given quantities and physical constants as appropriate. And so what is our first step? Our first step is we've got a free body diagram. Every single time we have a free body diagram, we want to think about F equals ma. In this case, we know that our acceleration is 0, therefore our sum of forces is 0. And therefore F tension, which I'll just write as Ft, plus F buoyancy must equal F gravity, and therefore our tension force is equal to force of gravity minus force of buoyancy. And at this point, in order to proceed, first we want to know what our given quantities are. So jumping back, we've been given the mass of the block, the volume of the block, and the density of the block. So we know M block, V block, rho block, and we also know the density of the water. So those are the quantities we can have in our answer, and as well as physical constants like G. And so beginning with Fg, that's easy for us to do. You probably have this memorized. Force of gravity is equal to mg. We know both of those. We've been given the mass of the block, and we know G. One quick thing I do want to point out is that if we were not given the mass of the block, we could still deduce it because we've been given the density of the block and the volume of the block. So make sure that you are comfortable with that step if you are not given the mass of the block. And so now to figure out F buoyancy, I'm going to quickly jump to my formula sheet. So looking at the formula sheet, we've got mechanics, electricity, and magnetism. We're dealing with fluids. So scrolling down, looking at fluids, what have we got? F buoyancy is equal to rho vg. So again, if you've forgotten to memorize this, right, you can pull it quickly from your equation sheet. But let's be a bit clearer with our formula. On the formula sheet, we simply have F buoyancy is equal to rho Vg. We want to be a bit more careful with our subscripts. Rho here refers to the density of the fluid in which we are immersed. V represents the volume of the object, which is submerged. In this case, though, the object is fully submerged. And so we use rho water for our density, and for V submerged, we can simply use the entire volume of the block. And there we are left with our answer, namely that the force of tension is mgb minus rho water V block G. So that concludes part one. We've dealt with buoyancy. Let us move on to part B. So we're now told that a monochromatic laser beam is incident perpendicular to the wall of the tank. The beam passes through the slit in the block. An interference pattern, we predicted that correctly. We're dealing with double slit interference, is formed on the screen inside the tank. The water is then replaced with a clear fluid with a greater index of refraction than that of water. In a coherent paragraph length response, describe how the greater index of refraction of the new fluid affects the interference pattern. Explain your reasoning in terms of speed, frequency, and wavelength of the light. So before we delve into this, let's quickly pull the relevant equations from our reference sheet. So we're looking at waves and optics, and we're going to pull a couple of relevant equations. First, we want our equation for index of refraction, since that's particularly mentioned. We want our double slit interference equation. And since something is specifically mentioned about expressing your answer in terms, or explaining your answer in terms of speed of wave and wavelength, let's also pull our general wave equation, lambda equals V over F. With that, let's jump back to our problem. So with our equation set up, let's dive into our reasoning. So the first thing we want to pay attention to is the question we're being asked, namely, how is our interference pattern changing? And so let's dive into our equation, d sine theta equals m lambda. And what we want to recall is that this describes a double slit with the slits separated by a distance d, a screen a length L away. Generally, L is much greater than d. And in the current setup, theta describes the angular position of a brightness fringe on our screen, where the angle is measured from the center of the slits, theta equals 0 being at the midpoint between the slits. And so this is the only form of double slit interference equation that you have on your equation sheet. But of course, we can very quickly simplify this if you remember your small angle approximation. We're going to consider y to be the midpoint between the two slits, or y equals 0 to be the midpoint between the two slits. And so now, if we want to describe the position of the mth brightest fringe, we can say that sine theta is approximately equal to y over L, so that we have dy over L equals m lambda. With that, let's pay attention to what changes when we change our when we replace our material with a greater index of refraction. So first, our slit distance hasn't changed, so d hasn't changed. L has not changed. We haven't increased the length between, or the distance between our slit and our screen. Y is what we're sort of trying to solve for, right? The positions of our fringes. M simply describes the number of fringe, right? So that's not changing. And so the only thing which could possibly be changing is our wavelength. And so that is what we're now narrowing down to. The question we're left with is, how does lambda change? With that, let's pay attention to what is actually being changed in the problem, our index of refraction. Now, index of refraction is equal to C over V. So if our index of refraction is going up, then V will be decreasing. And now we can pay attention to the consequence by looking at V equals lambda F, or lambda equals V over F. V has decreased. Frequency stays constant because it describes the numbers of crests per second. We can't have those disappearing. And so what we're left with is a decrease in our wavelength. So we've come to our conclusion, lambda decreases. Let's see the effect that that has on our interference pattern. So we're going to solve for y. Y is equal to m lambda L over d. Decreasing lambda means that our spacing between fringes decreases. We can see that our fringe spacing is equal to lambda L over d. And so if lambda has decreased, so has our fringe spacing. And so now let's briefly talk about how to construct this into a coherent paragraph length response. A general organizational principle, before you construct your paragraph length response, it's helpful to quickly write down the physical principles which form our bullet points. And so our first point is that increasing index of refraction leads to a decreased speed of light in our medium. Next, we argue that a decreased speed leads to a decreased wavelength, since frequency cannot change by our equation V equals lambda F. Lastly, we can then argue that double-slit interference equation tells us that with decreased wavelength, we have decreased separation between our interference fringes. With these bullet points listed, I'll leave it to you to construct a coherent paragraph length response addressing these points. Moving on then to part C, before we even read our paragraph, we can see that we've inserted a prism and we can see that there's some refraction going on. So we now get to our last predicted topic, Snell's law. And before even reading the question, we're going to quickly write down Snell's law, which you can pull again from your reference sheet in optics, namely that n1 sine theta 1 is equal to n2 sine theta 2. So we're told that the block is replaced by a triangular prism. We're given the initial path of our beam. And we're told that the beam, when bent by the prism, reaches point P on the screen. The fluid is then removed from the tank, and the prism is surrounded by air. So before we continue there, it's important for us to compare our two scenarios and have a good handle on what happened to our index of refraction. So scenario 1, here we're dealing with here we're dealing with N fluid versus N glass for our refraction. In scenario 2, here we've removed the fluid, so we're dealing with N air and N glass as our two media. And so we're now being asked to predict whether the beam will reach the side of the tank above point P, at point P, or below point P. In other words, are we going to get less refracted, more refracted, or equally refracted, which would bring us to point P. So now let's go through this with Snell's law. In scenario 1 and scenario 2, we're starting off in the glass and our incident angle will be the same. Note there's no refraction up until then because we're hitting all of our surface right along the normal, right, when we're entering the tank and when we enter the prism. So in scenario 1, we'll say N glass sine theta 1, or let's just call it sine theta. And in scenario 2, N glass sine theta. And set this equal to, in scenario 1, N fluid. Let's do sine theta 1, sine theta 2. And in scenario 2, we have N air sine theta 2. And we'll call it sine theta 2 prime, since we're interested in our new scenario. And so now this becomes a very simple question. Our question is whether theta 2 prime is greater than theta 2. If it is, then we know we'll be below point P. If it's less than theta 2, we'll be above point P. And so that just means we know that our initial scenario is the same. So N glass sine theta 1 appears in both our equations. I'll go ahead and equate N fluid sine theta 2 is equal to N air sine theta 2 prime. And lastly, What we know is that N air is pretty close to 1, pretty close to a vacuum, and fluid is therefore greater than N air. And so that leads us to conclude that sine theta 2, since the products must be equal, is less than sine theta 2 prime. And so theta 2 prime is greater than our initial angle. In other words, we're going to be more refracted and we'll end up at a point lower than our initial point P. And with that, we've finished problem 1. All of the predictions from our initial diagram indeed showed up as questions.